We were looking at the Lorenz system, and the main parameter is the Rayleigh number, R. And hopefully you remember what the Lorenz system was. X dot equals sigma y minus x. Y dot equals Rx minus y minus xz. Z dot equals xy minus bz. And typically we use the same variables that Lorenz did, which was sigma equals 10 and b equals 8/3. Something is related to the atmospheric model that he was concerned about. We found that for r less than 1, the origin, which is a fixed point, is the global attractor, meaning it's an attracting set of everything. So all initial conditions eventually end up going to the origin, which I would suppose means for a Rayleigh number less than 1, you don't have any motion for this atmospheric system. When r is greater than 1, if you remember from last time, we said the origin is a saddle, at least in the xy projection. So it becomes an unstable point is the main thing. So that was for r less than 1. We've got that situation, but what about r greater than 1? We're trying to find out what are the end states for different values of r and what can happen. And we're building up to the strange attractor that will be seen. And you can come to a conclusion that there must be this interesting two-dimensional strange attractor. So for now, let's suppose that r is greater than 1. The origin becomes unstable. Remember, it had 2 dimensions were stable and 1 dimension was unstable. And that's all you need is one of the dimensions to be unstable. It's not as clean cut as like the x direction is unstable. There's some directions in space. In the 2D world, you'd look at the eigenvectors. So the eigenvector corresponding to the positive eigenvalue is going to give you that unstable direction. And we had a pitchfork bifurcation. We've got that if we were to plot roughly location, this is a bifurcation diagram showing location of fixed points as a function of r. And they go from being the origin is stable to then it goes unstable. And you've got 2 branches that are actually stable. And following the notation of Lorenz, he called those C plus and C minus for convection. So you can show that C plus and C minus, those other points that grow out of the origin, are linearly stable, at least for a range of r. So for r greater than 1, and then less than a certain value, which is related to the other parameters, sigma plus b plus 3 over sigma minus b minus 1, which we call our Hopf, because there's a Hopf bifurcation. We're also assuming here, consistent with the parameters that Lorenz used, we're assuming that sigma is greater than b plus 1. If you put in the typical values for sigma 10, b 8/3, you could figure out what this Hopf bifurcation value is. It ends up being about 24.74. So when r is greater than r Hopf, you might think, well, maybe there's a stable limit cycle, but there isn't. If it was a supercritical Hopf bifurcation, remember the super part of supercritical means what's the stability of the new things, the new periodic orbits. In this case, this is a subcritical Hopf bifurcation. There is no stable limit cycle. The bifurcation is a subcritical Hopf bifurcation, which means that there are unstable periodic orbits that show up. So if we were to complete more of this sketch of the bifurcation diagram, we would get r has to be greater than or equal to 0. So we would start at, say, r equals 0. We've got a stable point till we get to r equals 1. And this isn't going to be a scale. And then the origin becomes unstable. You've got these 2 branches, call them Lorenz did, C plus, C minus. And then at some point, r Hopf, there's a subcritical Hopf bifurcation. So that those fixed points actually become unstable. And out of them, I'll do this in another color. There's unstable limit cycles. This is all schematic. So it's like there's this paraboloid of limit cycles, and I'm just showing one of them. So that's what's going on. You have it's at the same value. You've got this subcritical Hopf bifurcation at each of the 2 points, C plus and C minus. So if we're out here for R greater than R Hopf, and Lorenz himself looked at R equals 28. So that's greater than R Hopf. Everything's looking unstable. So where would trajectories settle down if everything seems to be unstable? So think of, you're tuning the knob of R. Trajectories must jump to a different attractor, but what can it be? You might be thinking, hold on, do they have to jump to an attractor? Maybe they're escaping to infinity, but it turns out, no, they don't escape to infinity. We'll ask it as a question. Do trajectories escape to infinity? If everything's unstable, do they just shoot off? You could answer this. We won't go through the calculation, but the answer is no. You can evaluate what the vector field looks like on some giant sphere surrounding the origin, and the vector field would be pointing inward. So you choose a large enough sphere, everything's pointing inward. It's a lot like the outer contour of the trapping region when we did the Poincare-Bendixson, but now we're talking about 3D. So it's anything that, any trajectory that crosses through that sphere from the outside is stuck. We've got a trapping region. So things must stay in some bounded region around the origin. They also are not settling down to a fixed point because the fixed points are all unstable. There's no limit cycle that we can see. The volume has to shrink down to something that has no volume, meaning if you start with a 3D chunk of initial conditions like that potato, right, it's going to shrink down to something flat, or maybe shrink down to a point, but at the very least, it has to have no volume. So something two-dimensional, and we don't yet know what it is. Things aren't escaping to infinity. Lorenz made an argument that there are no stable cycles in his paper, at least for the value that he considered. And we might look at that argument too. That's where he looked. He was out here, this R of 28. It's way beyond the Hopf bifurcation. So what are we left with? What else could there be? You might think, okay, things aren't escaping to infinity. They're not going to a fixed point. Lorenz argued that there's no stable cycles. Let's just take that on faith for now. What about, we've talked about quasiperiodic behavior. Maybe things don't settle down to something that's exactly periodic, but they would settle down on something quasiperiodic. Maybe. Could trajectories settle into quasiperiodic behavior? To do this, it would need to be on a torus. And I'll introduce some jargon here, an invariant torus, which means it's a torus, like there would literally have to be something that has the topology of a torus in the phase space so that you could have behavior where if you start on it, you kind of roam around, never coming back, because then that would be periodic. So if you're on this torus and you've got a frequency ratio that's irrational, you would have quasiperiodic behavior. This can't happen. You can't have an invariant torus. It goes back to the volume contraction. If there was a torus, so think of the torus bounds something inside, right? I got Play-Doh now that's not green, so you could see it. Or I could just bring a donut, but I don't have any donuts. I don't even have a bagel. I have one of those flat bagels, but they're not very torus-like. So here is there's some Play-Doh. It's gonna get on my fingers and get gross. So there has to be in the phase space something that is torus-like. Ooh, torus. And we're talking about, at least in this picture, it's just the surface of the torus. But if there is a torus that has a surface, there's also an inside. And so everything inside would be contracting due to the volume contraction. So you can't have this because everything inside the torus would shrink down, which includes the surface of the torus would need to shrink. So the answer is no, you can't have this. That's not possible. There's no quasiperiodic behavior. So what is there? What we're left with is things are bounded. It must be settling down onto something else that's not quasiperiodic. So this is that line from Sherlock Holmes that once you've eliminated all the other possibilities, then whatever's left must be the case. What are we left with? We're left with, it's not periodic, it's not quasi-periodic, it's not a fixed point, everything's bounded. Trajectories must, and I'll put settle into some other weird thing, an object of zero volume. So it has to be 2D or less. It can't be less, because if it was 1D, then it would be a periodic orbit. So it has to be 2D, and it wanders on that forever. And this is the famous strange attractor. If you were to look at what trajectories did, this is what Lorenz did. You could numerically integrate these ODEs with some initial condition, and the electromechanical computers of those days were unreliable and difficult to use. So he had to interpret his numerical results with caution, and that's why he made arguments like this. Lorenz started with an initial condition, x naught, y naught, z naught equals 0, 1, 0. So just starting 1 unit in the y direction. And then this is what he got. So you could see it starts with an initial condition over here. And then it did some excursion. And then you get these oscillations. And then it seems to be jumping kind of randomly from positive y to negative y. It doesn't seem to be repeating. So it's not repeating. It's also, according to the arguments above, not quasi-periodic, meaning if you were to do some Fourier analysis of it, you're not going to find a peak at two frequencies, omega 1 and omega 2. So we describe this behavior as a certain type of aperiodic. The common sense term is it's chaotic. It looks like the motion of that chaotic water wheel. Remember the angular velocity? The water wheel would be, rotating in one way, and then it would reach some tipping point and then start turning the other way. And then that's exactly what this thing seems to be showing. The water wheel was made later to try to understand in the physical model what this behavior was. So Lorenz wasn't thinking of a chaotic water wheel. He just had his equations. This is just a time series, right? Time series can be fun to look at, but we take the point of view of phase space, so we could look at what the phase space plot is. So if we were to plot what x and z were, and that's the projection that Lorenz looked at. So this is the z versus x. For this same trajectory, right, it started at 0, 0 on the xz plane. And you see what it's doing. It's sort of initially, it makes this big excursions, goes to sort of surrounding this left side thing, and it goes to the right side thing, and so on. I think around here, we would call this C minus, and around here, C plus. There's an unstable fixed point in there. The origin is also unstable, and it seems to be, there's this circulating around, and then every now and then there's these jumps from one side to the other, and then looping, and then kind of getting bigger loops, and then jumps. Let's look at the video. I think there's a video I showed in the first lecture. It just sort of shows an initial condition that's already settled down to this. And you can see what it's doing. It's circulating around and then jumping seemingly randomly. I mean, it's not totally random. It is chaotic though. So I don't know if this video, how long it takes to get to it'll do a time trace at some point. Yeah. So if you did a time trace of any of the coordinates, well, mostly X and Y, that's what Lorenz was thinking of. You could see this sort of, it stays on one, positive for a long time with these oscillations, and then it goes to negative. Z is kind of interesting. And Lorenz noticed something about Z. And we'll get to that. We could even sketch what the thing looks like. There's this really cool set of books by authors named Abraham and Shaw. I have it on my bookshelf somewhere, but it's basically just all pictures to describe nonlinear dynamics. And one of its pictures, they're trying to describe what the Lorenz system thing looks like. So this is just a sketch. This makes it look like it's some two-dimensional thing that folds back on itself. It's not quite two-dimensional like that. It sort of reminds you of a weird Mobius strip. This is just an artist's depiction of what, this is what things seem to be doing. This is from Abraham and Shaw. So this is just a sketch. The Lorenz Attractor, right? It's been called. It looks 2D. Later, when we talk about fractals, you could try to calculate what the dimension of this is, and it's something between dimensions 2 and 3. Whatever you want to make of that. I think the same thing is true if you take a piece of paper and crumple it up. Like when it's flat, it's 2D. And if it were a ball filling space, it would be 3D, but somehow crumpling it up makes it into a fractal, so it's something between 2 and 3 dimensions. It's got a fractal structure. I think Lorenz described it as an infinite complex of surfaces. So he was thinking of a bunch of 2D things kind of near each other, seeming to have a thickness maybe. I mean, I don't know how to describe what this is. This is weird. It's totally weird.